Okay, so in this very final vodcast on cosmology and on the astrophysics topic in total, we'll be looking at dark matter and briefly at dark energy. So these are the understandings. The ones in red we're not really discussing at all in these videos, as I said, because I feel that we discussed them sufficiently in the standard level cosmology course. So at the end of the last vodcast, we said that there is sort of conflicting evidence. There's a lot of evidence that suggests that the universe is flat. Therefore, the density of the universe is critical density. And we have a problem, because if we actually work out the observed density of the universe from everything we can see, all of the stars, all of the galaxies, all of the dust and gas and everything else, black holes and planets, it's not enough. But we have a solution. We have a solution to this. There exists, we believe, in the universe something called dark matter. Now, evidence for dark matter comes from various sources. One source is if we look at the rotation of stars in a spiral galaxy. Now, if we look at a star near the center of the spiral galaxy, then we can calculate its velocity by assuming that within its orbit, there is sort of a homogeneous bunch of matter, density rho, mass big M. The equation is gm over r equals v squared because the m's cancel. We can replace the big M with the density. So if you went a little bit further, if r increased a little bit, then m would also increase. We can rearrange that equation and we get that velocity is proportional to r. So that happens near the center of a galaxy, and we say that happens near the center of a galaxy because that is where a large part of the density is concentrated. So again, taking the value of, increasing the value of r slightly would increase the value of big M. That means that the velocity is proportional to r. If, however, we look at a star farther out, near the edge of the galaxy, then moving that little bit further, increasing that value of r, would not increase the mass particularly significantly. Instead, it acts a bit like the solar system in that all of the mass appears to be concentrated at the center of the galaxy. Okay, so there, v is proportional to 1 over r squared. So we have two different sort of velocity regimes. Near the center of a galaxy, v is proportional to r. V velocity increases as you increase the radius, but near the edge of the galaxies, v is proportional to 1 over r squared. Velocity decreases. That is shown by the red line on this graph here. So near the center, v is proportional to r. At the outside, v is proportional to 1 over r squared. That is what we would calculate. But that's not what we measure. Okay, and a couple of astronomers in the 1960s, 70s, and 80s first observed this. And it was thought to be a bit curious, but it did seem to imply that there was something else there. The explanation of this result is if you have a halo much bigger than the observed galaxy, that this dark matter exists. So dark matter is this weird stuff that, yes, it affects normal matter by gravity, which would explain these results, but we can't see it. It doesn't seem to interact in any way. It's not luminous. It's not visible. It's dark. It's not the only evidence. Something that we look at if you ever look at relativity is the fact that mass can act like a lens, bending light as it goes past. And in this picture, local nearby galaxies, such as these, are bending the light from more distant galaxies and acting like a lens, which is called gravitational lensing. And by running through the mathematics, we can calculate the amount of mass required for this gravitational lensing to occur. And again, what we see isn't nearly enough. There must be some hidden mass. Also, if we look at X-rays, we look at these galaxies, these are elliptical galaxies, and they're surrounded by clouds of gas. Now that cloud of gas is ordinary matter. We're not seeing the dark matter. We can't. It's dark. But the only way that gravity could bind such a big cloud of gas to that galaxy is if that galaxy had a much bigger mass than we can see. Again, there's missing matter, there's dark matter. So what is dark matter? We don't know. We have a couple of ideas. Some people have suggested machos. These are things like black holes, neutron stars, brown dwarfs, which are sort of failed stars, that have relatively high density but low luminosity. These objects exist. We can detect them by them doing little gravitational lensing, making stars behind them sort of briefly brighter and fainter. But we seriously doubt that there's enough of these to actually account for all of the dark matter. And don't forget, the dark matter has to be more than the amount of visible matter. For every bit of visible matter, there has to be probably 5 times the dark matter. Another possibility is what's called WIMPs, weakly interactive massive particles. The massive doesn't mean that they are actually massive, it just means that they have mass. So they do affect things by gravity, but in other words, in other terms, they're weakly interactive. They're like neutrinos. Neutrinos were long thought to be massless. We now know they do have a very small value of mass. And neutrinos are streaming through the Earth, through your body every moment, because they don't interact very much. There are other possibilities like axions and neutralinos. We don't actually know if these even exist. These are theoretical particles. And if these particles did contribute to the dark matter, there would have to be insanely large amounts of them, and there's no other evidence or models that would suggest that. So what is dark matter? We have some ideas, but we don't really know. And dark energy. Dark energy really is a mystery. We can estimate through those calculations involving gravitational lensing and gravitational binding and rotational losses, we can estimate the amount of dark matter. We can't see it, but through its gravity estimates, we think we know it's there. We estimate that there's about 5 times as much dark matter as ordinary matter. But even the dark matter and the ordinary matter added together do not make the critical density that we need. And yet the evidence suggests from the Planck observations that the universe is flat and has critical density. So this missing 68% of all matter that would make, and when we say matter, really we're talking about not just mass, we're talking about mass energy, E equals mc squared. So it's actually the mass energy of the universe which is needed to make the critical density. It's easier to think of it in terms of matter, but strictly speaking, it's mass energy. So the matter part of that is the ordinary matter and the dark energy matter, and at least part of the energy, or at least most of the energy, is probably this dark energy, which we think is what drives the acceleration of the universe that we've been observing. Okay, our current cosmological model is called the Lambda CDM model. Lambda is the dark energy, the cosmological constant that Einstein felt the need to create, which is expanding the universe. The CDM is the cold dark matter. And that model seems to be the one we have, but that's just a label. It's not really a description. 69% of the mass energy of the universe is dark energy, and we really do not know what it is at the moment. Hopefully you can find out and get your Nobel Prize. Okay, so that's the cosmology understandings that we've looked at so far in this vodcast. Thank you very much.